Right, a little bit different. We are in the hydrogen production. So our main field is on proton exchange membrane, water electrolysis, looking at liquid catalysis. And we do quite a bit of characterization on this, and especially on the mitigation of carbon emissions for decarbonization of steel, as well as in cement industry and other industries. So we are basically looking at the reduction of platinum group metals. South Africa is known for basically having 60 to 70% of the world's reserves in platinum, iridium, and ruthenium. But these catalysts are expensive. So we need to look at other resources and other metals. And in doing so, we're looking at suitable descriptive metals. And in those descriptive metals, just find my pen here, we will look at these metals: ruthenium, titanium, nickel, cobalt, and manganese, and in combination with each other, either as bimetals, trimetals, or alloys, like in 5 or 6 more metals, to see what can be done, how do we reduce the cost involved in electrocatalysis. We then have a characterization that's going to be followed with material characterization. Very important for this analysis is the actual D analysis, actual F analysis, the fraction and fluorescence, together with SEM, which will basically tell us about the distribution of metals and how the alloying has been formed. And then, of course, we will follow it with the transition electron microscope analysis for particle size. We also look at the electrochemical and physiochemical characterization that is utilizing cyclic voltammetry and linear scan voltammetry, because this will tell us quite a bit of information about redox potentials of the electrocatalysis, the overpotential, onset potential, Tafel slopes, and the corrosion and the kinetic rates. And then we're going to finally just talk a little bit about the construction what I'm currently busy with, and that is the implementation of a 1 kilowatt proton exchange membrane electrolyzer to take that further to the next step to produce the hydrogen, and then also the beatification of this hydrogen into the potential of ammonia or energy. Hydrogen is currently coming in different forms and different colors, different processes. And that is where the mitigation comes in, of how we can actually mitigate away carbon emissions and make it more suitable. Now, from a petrochemical industry, a lot of hydrogen has been produced from brown or black, which is basically from coal or use of gasification process, a lot of CO and CO2 emissions into the atmosphere. Gray, coming from steam methane forming, a little bit less carbon dioxide, but still these two categories is producing quite a bit of carbon emissions. And globally, that is a big struggle. We need to mitigate this and for depletion of our ozone layers and for mankind. Also, there is also blue, which is basically they're looking at carbon dioxide capturing from the stratosphere and then making methanol, for example. So that would be a good idea. That would be one way actually how hydrogen is produced today. And then, of course, there's the turquoise, which is a thermal splitting of methane through pyrolysis instead of CO and on a solid carbon base. So that produces even less. So this should be basically already start producing less and less CO2. Yellow, producing electrolysis using grid electricity. So you still a little bit of the background. There might be coal burning, diesel burning. You might produce your electricity. Hydrogen is from fracking or from natural sources. And then, of course, pink produced from electrolysis and nuclear. We are interested, however, in green hydrogen. Green hydrogen produced is basically predominantly from water splitting. And we're going to look at that more in detail in this presentation. And there's no CO2 emissions. But it's an expensive process. And of course, South Africa is also a water scarce country. So one need to look at of other ways, other means how green hydrogen can be produced, other than using green water. Where's hydrogen being produced? Why is hydrogen necessary? Hydrogen has been utilized in different forms as an energy carrier for storage and for all these other off-grid potentials. So first of all, look at the energy, driving of vehicles, supplying energy for the grid. That is from a fuel cell and driving cars predominantly, but then also you're looking at other processes like, for example, the decarbonization of steel, decarbonization of in the cement industry. So those type of things need to take place, right? Right, so therefore, hydrogen producing from these renewable sources, predominantly we're going to look at solar, PV, or wind energy. That can go to electrolyzer. The electrolyzer is with a splitting of water taking place over the membrane, which we will discuss in a minute. That's on a graphene. For those of you who don't know, that is basically a polymer that mitigate transfer predominantly hydrogen, and then the oxygen has been separated. And then, of course, the hydrogen can be utilized for fuel cells and other production, and then, of course, also been utilized to make ammonia and other sources. So what is PEM water electrolysis? So basically what we're looking at here is the reactions. It is the splitting of water, predominantly over this proton exchange membrane, which is graphene. And graphene is maybe not the ideal one. There's maybe some other polymers on the market as well, like aquaform and so on. That is perhaps a little bit better in the production. And it all goes about renewable energies and actually making the process less and less carbon free. But in this process, you're supplying electricity, or that is from the grid, or connected to a renewable energy like wind or solar, and you're splitting the water then into hydrogen from this reaction and in oxygen. So roughly that takes about theoretical potential of 1.23 volts. So keep this 1.23 volts in mind, because when we look at the electrolysis, that is what we need to just cross over enough potential to actually make sure we actually break that water molecule into hydrogen and oxygen. So we don't want to have a lengthy 1.6 or 1.8 volts where the overpotential becomes too large, because then it means you're putting in too much potential or energy into a system to split water. And of course, there's other thermodynamics of water electrolysis, like, for example, the entropy, the enthalpy that comes in for water splitting, and of course, your voltage there. Right, so like I mentioned, we need different characterization of parameters. First of all, the axotein, that will give you the phase angles and measurements. When you're looking at these different phases, like, for example, platinum and iridium, what goes more important, yeah, that's for pure metals. But what do happen when you're doing alloy? What do happen when you're doing bimetals? Either staying as a bimetal in the characterization, or they're alloying together and actually become a iridium metal oxide. And these speciations are very important because that can optimize your system. So we do XRD work. We're also looking at XRF work, and that will be mainly for element distribution and composition. And then, of course, a SEM and TEM analysis for your distribution, particle size that need to come in. Because particle size is quite important, because you don't want large particles, because you want to have a nice surface area where you have a nice distribution of the production, so you have a nice, even, and uniform structure where hydrogen can be produced. From an electrochemical point of view, however, we're looking at cyclophotometry. Now, I know there's a few electrochemists perhaps in the audience. That is when we determine the oxidation and reduction potentials of these metal species. And for hydrogen, for this project, it's important because that is the regions where we're going to look at hydrogen absorption and desorption. How do we actually mitigate? How much hydrogen can be absorbed? How many hydrogen can be desorbed or released in the system? We look at linear scan voltammetry. That will be potential. That is, like I mentioned, at 1.23 volts. That's a range that has been given there for overpotential. Now, iridium ruthenium, which is a benchmark metal, is roughly about 1.26, but we need to be stable and stay in that region of these platinum group metals when we actually look at the plots. Like, for example, a volt plot, voltamer plot, where you basically can determine what metals is necessary or can be used. Alpha slopes that can be determined from the linear scan, that is basically predominantly for the overpotential, the kinetics that is involved. And then, of course, we need to look at the durability. It is so important that these catalysts, and especially platinum proton exchange membrane, looking at about 6,000 to 10,000 hours. There's other electrolyzers as well, a little bit less, but that is what we need to look at. These things need to run continuously, especially when we're looking at the demand of hydrogen that is currently happening from 2025 to 2030. The escalation of hydrogen need for production for various processes is enormous. Here in South Africa, we're predominantly looking at, like I mentioned, decarbonization of steel and cement and other industrial processes. But other countries looking at running off the trains, for example, with a product that can run from hydrogen, from fuel cells, or SAF aviation fuel, or the production of ammonia or methanol that comes in. Just briefly in our process, what we're doing, that is for the fundamental understanding from a student point of view, that we're making these catalysts by basically looking at the precursor, like in the chlorides, for example, looking at the sodium nitrate, and that is called the Adams method. In this Adams method, they're basically oxidizing the chloride, the iridium to the iridium oxide, that then stirred for a couple of hours, dried, calcinated at different temperatures, 340 to 650 degrees. And then, of course, the ink is prepared from that, and we're running on our glossy carbon, we're running our cyclophotometry on linear scan. So that is what we're doing on a nutshell, from material testing, then the actual DXOF particle size analysis and electrochemical characterization, and then in situ testing with membrane electrode assembly. That is currently where we are doing quite a bit of work, where we're actually preparing these membranes and see how they can work in a unit. Right, just coming from the results. My results briefly is to look at it, and that is looking at the actual F analysis here. And then, like I said, the iridium ruthenium is currently the benchmark for the oxidation evaluation reaction, where platinum is very much the choice for the hydrogen evolution reactions. One can see here there's some very nice alloying forming between iridium and ruthenium. And this study was done predominantly to see how the iridium, which is basically 4 times the cost of ruthenium, can be reduced. Now, although ruthenium can be used as a catalyst, ruthenium in itself is not really too stable in the corrosive conditions. We're talking about here about pH 2 to 4 because of your electrolyte. Iridium is predominantly the catalyst that is stable, but is very expensive. And also very scarce in the abundance of the earth crust. So we need to find nice catalysts that can form nice alloys and characterize it. Right. We also have looked at iridium gold, already gold. Although we don't find too many alloying here, we find predominantly, like you can see the sharp peaks here, crystallinity and big clusters. They haven't really given us too much. And at today's price, I think gold is very expensive as well. So we actually have stopped working on iridium gold and looking at other metals rather that could be better. Iridium titanium have given us very good results. Now, titanium is also a metal that South Africa is mining and used quite a bit in cone making for airplanes, various production for titanium oxide for the paint industry. So there's lots of applications for titanium, but as alloying, it actually forms very nice. So iridium titanium already we're reducing the cost because titanium is much, much cheaper than compared to iridium, much more abundant. And that have shown quite a bit of interest in various electrochemical studies. From an electrochemical point of view, right, we have looked at the iridium ruthenium. There's our cyclic voltammetries. As you can see, there's some activity even in the low iridium cost, but you're losing some activity during the line. Iridium titanium also decreased. And then, of course, the iridium gold. Right, this is done in typical cyclic voltammetry cell, where we are utilizing a working electrode, which is our glossy carbon, which is impregnated with the ink of the actual catalyst, a reference electrode, and a platinum auxiliary electrode. The linear scan voltammetries have shown us quite interesting results, and that of the overpotentials, iridium ruthenium. And what we have found is a little bit of a bubble formation, and you lost that could split off quite easily if we not actually have the right techniques. So we actually have adapted our techniques to see what can be done. That is due to basically the formation of the oxygen and on the oxygen evolution reaction. And one can see the ruthenium It's quite nice at 1.24. And then, of course, you have the iridium 50/50 and the other as well. Iridium titanium, very nice onset potential here. A little bit more than that of the ruthenium, but still shows a very good stability. And of course, the iridium gold, show there that really not really too good results. It's been obtained with the gold, and that's also hence why we actually stop using that. Like I mentioned, it need to be done in a sulfuric acid because your electrolyte, your solid electrolyte, and I haven't got slides on that, is persulfonic acid. Right, so that's quite a bit of a low pH, and that needs to be stable. From these linear scans, what can determine our tafel slopes, right? The tafel slope is basically the plot against the log of the current density. And one can see here, this is our benchmark, iridium oxide, which is about 40.31 millivolts per decade. And then, of course, followed by the iridium gold and iridium ruthenium on the catalyst. We can get some reasonable good tafel slopes, good corrosivity, and good kinetics, because ultimately what we want is a low onset potential and low kinetics. Then you have very much a good catalyst that can then be tested on the MEA and do long-term stability testing. Right, electrocatalysis. This is a nice summary of what we've done so far. And this year, my students are actually looking at trimetals as well as up to 5 metals to see what is the ideal optimization with these low catalysts, and are they really as robust as iridium on their own, as iridium ruthenium, right? Which is, like I mentioned, the benchmark. So catalyst, there's your reductions in the iridium content, 20, 30, and 50%, right? And in each one we have done more or less the same to get reducible results. The area, the scan rates that we utilize, mass to the catalyst, and then of course potentials, and then the current densities that has been obtained. From that, we need to work out our capacitance, so we can actually from there determine our EXA, which is basically electrochemical surface area. However, from these results, one can see that the onset potential has become very large. And remember, we said about roughly about 0.23 to 0.28. Although it's 1.8 is still in the ballpark, we felt that it's a bit high, although they have given us good results. The onset potentials here for ruthenium is very much close to your theoretical, which is 1.23, and then of course that of the gold. Our potentials, like you can see there, is roughly very small, and then you get a little bit larger here. And of course the tafel slopes, that is where the problem lies, especially with the titanium. And we have really looked at some of this data to make sure that we are seeing is correct. Right, so that is on electrocatalysis. So we actually, at this point, we are doing quite a bit of other work, like I mentioned, on other catalysts. We want to spread our wings a little bit more on this, also on the material side. And we also want to bring in the power spectrum, the XPS results, to actually do speciation, because I felt that is quite important when we're looking at optimization. The next part of this investigation will be to actually really produce hydrogen on a bigger scale. For this, I actually built this demonstration unit, and actually this flow diagram just shows what we are basically looking at, and that we will have a tank, maybe even seawater, that can go through a desalination plant. Then it goes through a RO system, basically to remove any unwanted material, because the proton exchange membrane is very sensitive to other materials, CO, CO2. It can deactivate quite easily the catalyst. So you want to remove as much as possible organics and other debris that can deactivate your catalyst. So that goes through a reverse osmosis system, an exchange, and an activated charcoal system. And then it'll be pumped into a hot water system where it can actually heat up to about 60 to 70 degrees optimum temperature. That then goes through to an electrolyzer, and an electrolyzer now that is connected to a renewable source, like I mentioned, the solar panel in this case, and that electrolyze the material, and then from there you'll get your water splitting, And that goes into how we save our hydrogen, and then you basically can remove the water that's trapped, as well as the oxygen that goes into the stratosphere, unless we find a suitable buyer for that oxygen. But hydrogen again goes through a drying stage, and now we can use the beneficiation of that hydrogen in the potential of a second phase of this project. What we are thinking of is the ammonia production. And that can either go into ammonium hydroxide or ammonium nitrate or ammonium sulfate. And if you know a little bit of general chemistry, that is first for fertilizers and other processes. On that front, this is our unit. As the flow diagram, we have a potential state in the bottom here that goes through our electrolyzer. Now that is a 1 kilowatt cell that I bought from the States. And the reason for this cell is basically it can actually open up and we can actually exchange our own membrane in here and do proper testing. That is our oxygen cylinder, where we actually capture our oxygen. And that can be utilized for other processes or go into the atmosphere. And then, of course, the hydrogens would be recovered. And then we can work out the hydrogen efficiency from here, photonic efficiency, and then goes through a drying tube. And then it be captured in our storage unit that can then relay that to an Haber-Bosch process or a reactor where we can do the Haber-Bosch process to make the ammonia or other processes. This ties up very much to what industry is doing, because that is our big emphasis here, not only training postgrads in the master's PhD level postdoc, but also engaging with industry to see where we can go and how we can actually help them with the necessary processes, also catalyst development for these processes. Because manufacturing is globally quite a challenge, and that we need to address. Right, we've done some durability study on this unit. That runs for about 8 hours. So we can see it's quite nice and stable. More of these studies will need to be done on a longer period, and we wanted to push that, like I said, 6,000 to 10,000 hours is ideal to see where it will pile off. So that will give us a nice activation energy, and it will give us a nice see where this operation temperature is before we actually start piling off. So this is a durability study. There's a typical chronopotentiometry. All right, so what we can take home from this is we want to overcome anaerobic electrocatalysis, especially in the OER, the oxygen evolution reaction. And like I mentioned, it's a global challenge, especially in the hydrogen economy, to do that. Platinum group metals or proton exchange membrane is probably not the only one, although it is the best one at the moment, but there's a lot of work being done on ion exchange, alkaline electrolyzers, and solid oxide electrolyzers, because I think it's going to be a combination of these electrolyzers to reduce the demand of hydrogen that's necessary. We'll investigate a single MEA or the membrane electrode assembly to determine the best suitable OER in the in situ situation, where we can actually see what is happening at the interfaces between the hydrogen evolution and the oxygen evolution. And how robust is these catalysts over a long time period. We look at the aims of the longer term development, manufacturing know-how, production, and especially on the MEA fabrication. There's a lot of ways how MEA can be done, where you spray the ink on the anomina, for example, the polymer. That can be done by spraying, and some are using inkjets. So that is one of the things that we want to use. Nationally or internationally, that's been done in the States and China and a lot of other places doing MEA, but there's not really too much manufacturing here in South Africa. So we want to really export and look into that. And then, of course, looking at this demonstration unit, and if it works on the 1 kilowatt, even try it on a 5 kilowatt. Try to enlarge it, but then, of course, go to the next stage, which is looking at the ammonia production or methanol production. And we have quite a bit of nice catalyst already on that can cook very well with the Haber-Bosch process or the methanolization process. That's the students that are currently working on this project, masters and master students. And they have done quite a bit of the work on the electrocatalysis, on the characterization, and then want to take it further to the next project, the next stage. However, we need to always thank our sponsors. So this is quite a bit funded from the National Research Fund. I got quite a bit of money from that, as well as from the TIA, which is the Technology Innovation Agency seed fund to do this project. Our Research Development Fund at the university itself for their support, students, And of course, I want to thank the conference, Alexander, for inviting me to this, and you as the audience for listening to me. Thank you very much for your attendance.